In this video, I'll cover correlation analysis. So correlation is a term that has come up a few times in this course. When we were learning about types of reliability, we touched on this briefly when we said that parallel forms reliability, inter and intra-rater reliability, and test-retest reliability can be assessed with correlation analysis. We also talked earlier in the course about research designs. We said that correlational design is one in which the researcher does not manipulate any variables. It's non-experimental. Basically, the researcher just collects observational data on two or more continuous variables. For example, in cars, we might record horsepowers and gas mileages of cars and basically just do an analysis to see if there's a linear relationship between those two continuous variables. And what we found was that horsepower and gas mileage are negatively related. So the coefficient is negative 0.776. The p-value is less than 0.05. It's actually less than 0.001 as well. So a significant negative correlation, meaning that cars that have better gas mileage have worse horsepower, and vice versa. So cars that have better horsepower have worse gas mileage. So the correlation coefficient, in our example, negative 0.776, needs to be between negative 1 and 1. It has two components. It has a strength, which is basically its magnitude. The closer it is to either negative 1 or 1, the stronger the linear relationship. The closer it is to 0, the weaker the linear relationship. It also has a direction or a sign, so it can be either positive or negative. If it's positive, it means that as one variable increases, the other one also increases. If it's negative, it means that as one variable increases, the other variable decreases. And at the bottom of the screen, you can see some examples of scatter plots, that basically how the data would appear on a scatter plot for different levels of correlation, again, whether they're negative or positive. To interpret the correlation coefficient, you do need to be mindful of the way in which the variables were scored. Sometimes it can be misleading if like a lower score means better, then you may see a negative correlation when you're expecting to see a positive one. So for example, if you hypothesize that there's a positive correlation between hours of practice and performance in a sport, which makes sense, it's common sense, but it's also supported by research. And let's say that you're looking at golf scores. So in golf, lower scores mean better performance. So a negative correlation between hours of practice and golf score, meaning that the more you practice, the lower your golf score, would actually support the hypothesis of more practice, better performance. So that's a pretty simple example, but you can definitely see some examples in published articles where you may see a correlation coefficient that's negative when you expected it to be positive, or the reverse. And you may just need to do a little bit of additional digging to see how they scored the variable, like how the questionnaire assessed whatever it is that they're looking at, and basically figure out whether that correlation supports the hypothesis or not. And obviously the author hopefully will explain that clearly. So here's a correlation table from a published article from Shen et al. In 2007, where they're basically looking at correlations between a lot of different motivational variables. So I just wanted to kind of go through how to read a table like this. So I'm going to pull up my laser pointer quickly. So the way this is organized is it lists the 10 variables that they were examining, and then it uses the same numbering across the top. So what you see here is the correlation between variables 1 and 2. So between pre-knowledge and pre-skill, there's a significant correlation of 0.45. You can tell it's significant because there are two asterisks here indicating that its p is less than 0.01. Here's an example, the correlation between mastery goal, variable 3, and performance approach goal, which is variable 4, is the correlation is 0.19, and that's significant at the 0.05 level. P is less than 0.05. So you get the idea. You can go through and look at all the different correlations. Here we see a 0 correlation, but really any of the ones non-significant can be assumed to be possibly 0. There's no correlation between the variables. So we see an example of that here with variables 5 and 6. Performance avoidance goal and individual interest are not significantly correlated. The coefficient's 0.07, which is non-significant. So how many correlations are there? Well, certainly you could go through and just go ahead and count all of these if you want to. But if you're planning a study and you have so many variables that you're going to be looking at correlations between, and you want to know how many correlations are you going to be looking at, you could basically use this formula here. So if P is the number of variables, then you basically just take P times P minus 1 and divide that by 2. So in this case, we have 10 variables. So P is 10, P minus 1 is 9, 10 times 9 is 90, divided by 2 is 45. So if you were to pause the video and count all of these, you should get 45. But that just helps you to plan out how many correlations you would be looking at between however many variables you have. So correlation certainly has its limits. So one of those that we talked about earlier in the course was the idea that in a correlational design, it's not possible to establish a cause and effect relationship. You would need to do an experimental design in order to possibly establish a cause and effect relationship. So here's some examples of correlations that certainly don't reflect any sort of causality. So ice cream sales are correlated with the number of birds in trees, the number of cars parked near the beach, electricity expenditure, and the number of violent crimes committed. And I'm sure you can guess what other variable is actually influencing all of those, which is the season or the weather. The basically warmer temperatures will lead to or will contribute to all of those different increases. So with correlation, it could be that X causes Y, it could be that Y causes X, or it could be that some third variable Z, in this case the weather, the temperature, the season, influences both, for example, ice cream sales and the number of violent crimes committed, which are obviously not directly related to each other. Another limitation of correlation analysis is that it only considers linear relationships. So in this case, in this graph that you see here to the right, there's a clear patterned relationship between the variables X and Y, but if we use correlation analysis to see if there's a linear relationship, we'll find that there is no correlation. The coefficient is negative 0.03, it's non-significant, there's no linear relationship, although there is another type of relationship, and in this case it's a cosine wave, but basically correlation would not allow us to see that relationship. A third limitation of correlation is that it's highly influenced by outliers. So in these two graphs we actually have the exact same data except one additional outlier in this graph over here. And because that outlier is there, it's basically pulling the line of best fit in this direction. So it appears as if there's a positive correlation of 0.6077. If we remove the outlier and reanalyze, we would find there's a weaker relationship, but it's a negative relationship, negative 0.196. So here we can clearly see the outlier is basically, making a big impact on our analysis. Another example, here's the outlier. Otherwise, same data shown over here that's shown over here. With the outlier, it's looking like a weak positive relationship, 0.182. Without the outlier, it totally changes. It's a much stronger, but still positive relationship of 0.90. So it's possible in this case that it would be non-significant. It would be basically no different from zero. But in this case, it's likely to be significant. So to wrap up, I just wanted to connect correlation with what we've learned earlier about null hypothesis significance testing just by going through the 4 steps of that. So as an example, in an earlier semester, I collected data on how long it took my students to complete their exam. So basically each time a student turned their paper in, I recorded the number of minutes that had passed since the beginning of the exam. And then I recorded that data, and after I graded the exams, I looked to see if that correlated with their score on the exam. So basically, is there a relationship between completion time and performance on the exam? So the first step is to state the hypotheses. And for these, I'm going to use the Greek symbol rho, which is basically like an R in Greek. It looks like a lowercase p, but it's actually an R in Greek, or a rho. So rho equals 0 is my null hypothesis. Rho does not equal 0 is my alternative hypothesis. So basically, the null is that there's no correlation. The alternative is that there is a correlation. I'm not making any prior assumption about whether that correlation is going to be positive or negative. It could be that students who complete the exam in less time do better on the exam. It could be that students who take more time to complete the exam do better on the exam. I'm not sure. Or it could obviously be the null hypothesis, which is that there's no relationship. So the second step is to set the critical value. And again, that's based on the sample size, so it depends on how many students I had in the class that particular semester, and the alpha level that we choose, which is, in this case, 0.05. That's our significance level. So on the basis of those two numbers, we can find the critical value, which is 0.433. So basically, we can add those to the graph here. So basically, any correlation that's beyond negative 0.433 at this end or positive 0.433 at this end is going to be strong enough evidence that the null hypothesis is unlikely, and therefore we will reject it. However, what we find when we calculate the test statistic, R-obs, is that it is not beyond those critical values. It is within the non-rejection region. It's close to 0. It's actually 0.051 is the R value. And the p-value is 0.826, meaning that based on our observed data, the null hypothesis is not all that unlikely. It's likely, basically. So our decision whether to reject the null hypothesis is to not reject the null hypothesis. It's to retain the null hypothesis. Basically, the evidence does not support the notion that exam score and completion time are correlated. And we can see that pretty clearly looking at the scatter plot as a visual. You can basically see, okay, certainly we have some higher exam scores. We certainly have some lower exam scores. We have some moderate exam scores. And we also have a range in how many minutes it took to complete. So the minimum for that was 35. Basically, the first student to hand his or her paper in did so after 35 minutes. There were other students who took about an hour to complete the exam. Yeah, so there's just no pattern. There's no linear pattern that this line of best fit follows. There's no clear relationship between exam score and completion time, which is reflected in our R value, our coefficient that's very close to 0, and our p-value that is clearly greater than 0.05. So no significant correlation between completion time and performance on the exam. And that's it for this video. Thank you very much for your attention, and I will see you soon.